what I'm going to talk about today is a joint two pieces of work that we did together with Valery Ogrinovsky and Ian Peterson, which was very entertaining and interesting from my perspective. We learned a lot, and we made some strange connections across the different fields. And it's very good to work with people that are smarter than me. I learned a lot. Okay, so what I'm going to talk about is heavy ball method is something that is beaten to death. So I continue that tradition, but it's very well misunderstood as well at the same time. So there are certain things about it that turned into a bit of folk theorem, grandmother's tales, whatever, old wives' tales, whatever analogy you want to use. So hopefully I'm going to try to clean up stuff the way that we understood it. Okay, the overview of the talk. I first introduce the questions of interest. I go through some of the preliminaries we need. And then I ask two questions. These are the questions we are going to ask. They make more sense later after I cover it a bit. And then I finish everything with the conclusions. Okay. So the context of the problem is an optimization problem in the context of we have no constraints. We want to find we want to minimize some cost function fx. And the method that we are going to focus on is this heavy ball method due to Polyak. He proposed it in the 60s. It is related to this other thing called the Chebyshev model method. Polyak was built a lot of the theory and introduced in the late 60s, mid-60s. So the idea is this: my iterates are generated by a traditional, forget about the term, with the coefficient beta, is a gradient term, and the coefficient beta brings some memory of the previous iterates into the current iterate. This is a term that is commonly known as the momentum term. The intuition behind it is that if you're following the gradient, or the negative of the gradient, you want to, and assuming that you were traveling along the right direction, you want to accelerate by doubling down on the previous direction. So that's the intuition behind the heavy ball method. And this momentum term is thus the heavy part of the ball rolling down some slope. The standing assumption that f is differentiable is potentially non-convex. I will talk about what I mean by that. And grad f is just a nabla f is just a gradient of f. And then these parameters are some positive scalar constant. They are the step size of the algorithm. So the first question that I'm going to ask is, does remembering more than one step lead to better convergence results? So for example, take this other algorithm. It has the gradient part, it has the first momentum term. And what if I remember one extra step? If I'm assuming that remembering the previous direction of travel was good, why not another term? Would this lead to a better performance? I'm going to define what I mean by performance, but think of it as rate of convergence than the vanilla heavy ball method. Now, what about adding more memory terms? What if I say I want to remember 10 steps before? What can I say? And then I will talk about, and I will ask another question in the second part of the talk. Something that we know about heavy ball is that the stability convergence proofs for heavy ball are local. And again, they are due to Polyak itself. Can we come up with a way to select the parameters so that we have global results? And when I talk about global, I'm talking about uniformly globally stable. I'm not talking about global meaning optimization. I'm talking about convergence of the algorithm from any initial condition. I'm talking about that in that sense. Or can we select these parameters optimally so that they yield the best performance that you're interested in? So these are the two questions. Okay, let's see some backgrounds and preliminaries. First, I talked about performance. So the measure of performance that we are going to use is this thing called R convergence or root convergence factor. So if I have a sequence of xt generated by some method, so just a sequence xt, and I assume that the sequence is converging to some limit point x star, then this number, which is the lean soup of t going to infinity of the distance, the 1/t root, is something that is known as a root convergence factor or R factor of xt. So it's really an asymptotic measure of convergence. The other definition that I'm interested in is when I talked about a uniform convergence and uniform convergence idea is that assume I have xt that is just the iterates of an algorithm at some step t, initiated at time naught. If I have multiple memory, I initialize everything in the past as well. Then the algorithm is set to converge globally asymptotically to some x star if the iterates have the following properties. It's a typical epsilon delta definition. It's the uniformity of for every epsilon there exists a delta type argument. It's really just limits. And the second is more explicit. The distance to that initial limit point goes to 0 for any uniformly in any initial condition x naught or anything else if I have a multi-memory method. So these are just the sort of language that we're going to use. Okay, now the convergence of the heavy ball method, if you go and pick up Polyak's original paper, this is where the arguments, how the argument is constructed. One of the ways of the proof that was constructed was for the case that f has a Hessian, that if I evaluate the Hessian at the limit point of, or some stationary point, let's say, if the Hessian is lower and upper bounded by 2 diagonal matrices, and scalars of identity. And it is known that for the heavy ball method, the root convergence is always less than this rate that I'm going to call R subscript P is the rate of the Polyak, given by this ratio square root of L minus square root of M divided by square root of L plus square root of M. When it is initiated sufficiently close to x star, that's the local convergence result that we have. So if we initialize the heavy ball algorithm close enough, now there's closeness, you humor me for a bit, close enough to x star, then the rate that I'm going to converge to x star is given by that RP. This quantity is the root convergence factor for the sequence. And then when we restrict the set of F to only include quadratics, and I'm going to call it Q, and is the dimension of the space, M is this lower bound, L is the upper bound, then the heavy ball method converges globally. So if I look specifically at quadratics, I have a global convergence result. So I don't, it's sufficiently close, then becomes everywhere in the space. And then the inequality becomes tight. So the root convergence is exactly this rate of. Okay? So these are the things that we have known for 70 years, 60 years. Now, this is where things become a bit confusing. The problem is, what we see here appears in other places as well, which makes it very curious. There is this result that is often miscoded. And at least that's what we realize, is that if you go and look up, it appeared in Nesrov's book, I think, introductory lectures to optimization. Which I don't know what is introductory about them. I don't know. There is this theorem in chapter 2 that shows for infinite dimensional problems, we will have a similar rate of convergence as a lower bound. Specifically, it shows that among m strongly convex continuously differentiable functions with L Lipschitz gradient defined in an infinite dimensional Hilbert space, then there exists a bad example of a quadratic function for F so that we cannot beat this rate. So that is known as the Nesterov lower bound. The key is infinite dimensional. The proof there is for infinite dimensional systems, and then there is a line in the book that says, similarly, it can be shown for finite dimensional cases. That's not correct. Because exactly if the example of the bad function is quadratic, we know from Polyak analysis, that's the example of a good function in the Polyak case. So it's not quite, the proof doesn't go through. In fact, if we go and look at attempts in stating a similar result for finite dimensional problems, the results is due to Nemirovsky, his 1994 book. A similar statement can only be made for the first T steps of an algorithm applied to a finite dimensional problem when T is less than or equal to the dimension of the space plus 1. So we don't have anything about, again, maybe these results exist. It's a very strange landscape of results, but we don't have anything. Seems that there is no results about asymptotic rates. And when I have, it is a bit odd to stop an algorithm at the steps it's less than the dimension of the function that we are looking at. So that's where we wonder if people intuitively assume this rate, this bound translates immediately to finite dimensional problem, but it wasn't clear to us at all. Now let's ask that question. It's really a question of this fundamental lower bound. Is it possible to break this lower bound or not? And another way of asking that question is, can we get something better if we remember more about our past attempts? Yeah.
Question. So I didn't get that. It was never proved that there's a lower bound except for infinity.
Yes. For infinite dimensional problems.
But the opposite wasn't true. They hadn't said when it's finite, there is a proof that.
Yeah.
Okay.
Okay. So then all of these things have led the community to believe that in optimization of quadratic functions, no other first order method can provide a better root convergence factor than heavy bond. That's the conclusion that the community has. But the thing is, the conclusion cannot be drawn formally from existing finite dimensional results because they don't hold as T goes to infinity. There's a gap. If we fix the dimension of the space. Now, in what follows in the next 10 slides, we use the resultant robust gain margin of linear uncertain feedback control system to show that heavy ball method is provably worst case asymptotically optimal when applied to quadratic functions in finite dimensional space. So it's a bit anticlimactic because the band is really a lower band in a particular sense, but at least now we are trying to construct a reason. It would be great if you could say, now there is this other lower band. Okay, let's consider the set of finite dimensional quadratic functions. I use this Q sets to represent those. They have band adhesion in M and M. Let's introduce this generalized multi-step method. It remembers k steps of the previous iterates and remembers L steps of the previous gradients as well. So we just bring all the memory with us. And then the output is some combination of previous observations. This is just a generalization. This allows us to write things as over-relaxed algorithms. So we assume the number of past iterates that we remember, k, and the number of past gradient evaluations, L, can be set arbitrary in an arbitrary way, but they don't change with time. So once we design the algorithm, we fix those. And these coefficients are a scalar constant as well. So that's the standing assumption. So the machinery that we are going to use is just, you don't need to worry about this. If anyone's interested, I'm happy to share the slides. You can look at the paper. But really the most important observation is we can rewrite the algorithm as a Lura type nonlinear dynamical system. A Lura type, simply put, is something that without, if I forgot the input part, let's assume it's a linear system, but the input is a nonlinear feedback interconnection of some output vector. So that's a Lura type feedback interconnection. And there are results around it, right? People have studied these things. The other thing that we assume is that we make these two technical assumptions about the coefficients. These assumptions are, they hold in many practical cases. For example, in Nestrov's constant step size accelerated gradient method, L is equal to 0. L is how many previous gradients we remember. K is equal to 1. How many previous steps we remember. We set alpha not equal to 1 over L, beta not this thing. Then we have a bunch of other variables there. Again, this, as if you remember, these are the weights of how we mix the previous iterates to construct the output of the algorithm. Really, we are saying we do a convex combination style of the previous iterates. Again, if anyone has looked at these over relaxations in the algorithm, that's what it is. Now, under this assumption, we have a fairly straightforward lemma that if f has a unique stationary point x star, these assumptions lead to the fact that x star is the fixed point of the generalized multi-step algorithm. Then this follows through that this capital X star is the unique equilibrium of the Lura system. And if we now look at an f that has a quadratic form, delta in the middle, and there we can do a change of variable. X bar is the error vector. We end up with a fully autonomous system. It's a linear system. The thing is that delta appears in the coefficients. And we are interested in any function f of this type, and we know delta satisfies some lower bound, upper bound, and its eigenvalues. So this, in robust control sense, that's the uncertainty that enters the dynamical system. We know that the stable is system if and only if the spectral radius of this matrix A bar, which we use rho of A bar, is strictly less than 1. So it's a Shor matrix. And moreover, this spectral radius characterizes the degree of stability of the system. In other words, it's when the system is stable, the states xt approach the fixed point at least as fast as rho of A bar to power t. This is the rate that we are there. In terms of R convergence, the R convergence rate is exactly the spectral radius. So we are trying to, again, none of these things are earth-shattering, but we are trying to bridge these sort of terminologies across different disciplines, right? Okay. Now let's see. We can now study the method as control of uncertain systems. When the function f is not known, and it's only known that it belongs to this class, so that's really, we end up having an uncertain system with a parametric uncertainty that satisfies a bunch of conditions. So what we are really interested in the stability for all choices of f. And the degree of the stability of the system in face of this uncertainty is the supremum of among all the possible spectral radii. If I go and pick any function, plug it in, calculate the spectral radius, that's the worst case convergence rate. You can think of it like that. Because, so if I now look at the behavior of the trajectories xt as they converge to x star, across all the possible systems I can get, it would be at least as fast as this supremum topology. So it's about characterizing the behavior of a class. Then we can define the worst case root convergence. Supremum of f across all of these things would be supremum of the spectral radius of that A bar object when the uncertain parameter belongs to is larger than m times identity and smaller than L times identity. All these inequalities are with respect to positive semi-definite corners. Okay. Now we can state the theorem. Worst case, R convergence lower bound. They're saying for any k larger than or equal to 1, k was how many steps of the iterator we are going to remember, and some L between k and not, and 0. Any collection of parameters, these are coefficients that we use to construct that generalized multi-step algorithm. So that they lead to a converging method, satisfy this relationship. So the worst case convergence rate, which is the largest, the supremum of these spectral radius, are lower bounded by exactly that RP. Now it's a bit of a, looking at the theorem, it's a bit magical, but we can dig a bit deeper. The proof of this theorem employs the result of Carbonnecker and Tannenbaum from the 1985 result. I think it was one of the first Tannenbaum's results in linear systems theory. And Ian told a story about that result. Apparently his uncle gave that question to him. And Tannenbaum was a mathematician, so he solved it. His uncle was more traditional computer. That's this sort of things that you have when you work with people that were around in the 70s and 80s. And it was about robust gain margin of linear feedback control system. Gain margin, in the way we are thinking about it, is exactly the spectral radius. So if I really manage to shrink the ball that my eigenvalues live in, I have a big margin from the boundary of circle radius 1. That's the intuition behind that, right? So we want to design a controller that really pushes all the eigenvalues in a ball as small as possible. And in a special case that is, we give it here, and this special version is the one that we use. The proof, in fact, clarifies how it is related to even an older problem, which is the Naven-Lina peak interpolation problem. It's really just how to interpret a polynomial. Why do we care about polynomials? Because characteristic equations of matrices are polynomials. And the statement of the results is given here. Imagine I have a plant P, it's an integrator. Now for the students in the audience, can anyone tell me why it is an integrator? Any optimization algorithm, if you write it as x something, xk plus 1 equal to xk plus some update is an integrator. So the plant is an integrator. We have a constant gain, but it's uncertain, lambda. Lambda is this matrix coefficient that we don't know. Links between M and L. And we have a compensator. Kz, that's the controller. Kz, the order of the compensator, really determines how much memory we have when we bring it into the system. A proper real rational compensator K that places all poles of the system in the interior of this disk less than rho exists if and only if we pick the rho to be larger than RP. So we cannot design a controller that makes brings all the poles inside a disk of a radius less than RP. Yes?
Kind of the small gain theorem.
Small gain theorem is about, it's a sufficient condition that talks about stability of feedback interconnection system. That's another sufficient condition.
Oh, okay.
It's about this is about designing a system that satisfies a bunch of conditions. They are related, but it's not exactly the small gain. It's really, this is a question of what is possible in principle. Can we ever beat that rate? So the answer is no. Okay, we are halfway through the talk. So what we notice is adding more memory doesn't help. And it's an if and only if condition, so it's as tight as it comes. Now, okay. All is good. Some other thing that we noticed is, when I talked about it, the heavy ball method is not uniformly global asymptotically convergent. Now, is it possible to choose the parameters so that it is? So we know heavy ball in this notion of best is the best that you can get, but now what can we say about it? So for the next 14 slides, I'm going to talk about the behavior of HBM, the heavy ball method, in terms of its global convergence for a class of non-convex problems. We are interested in designing picking the step sizes so that the method is globally convergent, and we get the best R convergence factor. And we in fact show that for a family of cost functions, this convergence factor is superior to the factor obtained from the state of the art, which is the triple momentum method. If anyone's interested in this paper. Now, if you notice, when I gave the talk, the first part is going to appear in 2023. The second part has appeared in 2022. The reason is when we submitted the first part, because we made this statement that this result doesn't exist, the reviewers didn't like it. They said, no, it obviously exists. And they recited what we cited as an evidence, which was a bit odd, but the first time we got like that, said somewhere else. Now I'm going to go on a rant. I think as a community, we sometimes radicalize ourselves to accept certain folk theorems without knowing where they come from. So maybe we should have accepted it. It was very surprising for us, but yeah. Anyway. Okay, what we are interested in, we said non-convex, but it's different. There is this code I think, ascribed to Fletcher, that says the watershed moment between, in optimization theory, is between convexity and non-convexity. What I think is between benign non-convexity and ugly non-convexity, however you want to define it. So I'm going to show you something that is fairly benign convex, non-convex function. But that's a class of functions we are interested in. They are not globally convex. They are only convex in an infinitesimal small region at the vicinity of the stationary point. And specifically, we are interested in functions that satisfy a sector condition. This is the condition. I'm going to show you what it means in terms of a picture in the next slide, but they satisfy this, they satisfy a sector condition. Now, let me show you the picture. A sector condition, the gradient of a function satisfies the sector condition if, for example, it remains between these two linear subspaces. Okay? So this is the function. If I calculate this gradient, it looks like this, but the gradient is bounded. It is bounded below and above by two linear subspaces. So this is the function that we use to construct this. And these are the sort of sector conditions that we are interested in. If the gradient is monotone, then the function would have been convex. But it doesn't need to be monotone. As long as it's bounded, these are the primary functions we are interested in. Now, this particular function is invex, if anyone is interested. Invexity is not the same as quasi-convexity. This is another word that people use. These classes don't quite overlap perfectly. But of all of them, we are interested in all of them that satisfy the sector bound condition. It's something I've been talking about with Anton. Again, this is related to a condition, Polyak-Voyazovich condition. That's again, not surprisingly, this is a Lura system as well. We knew for the generalized case, it's a Lura system. Of course, for the special case, we still will end up with a Lura system. And all those results will follow through. And in fact, it's easier to actually write. The feedback interconnection is this nonlinear feedback interconnection through the gradient of F. Again, it is well known that the Heavy-Ball method, the minimal value of R factor is achieved for these choices of alpha and beta. And this is the rate that we always get. I just keep reminding you of that. And then we have a theorem that derives a range of ratios L over M for which the Heavy-Ball algorithm with these choices converges globally for all the functions that satisfy a sector band. So if the ratio L over M is less than this threshold kappa naught, which is 3 plus 2 times square root of 2, then the Heavy-Ball method for these choices of parameters globally asymptotically converges to X star. Now, where this thing comes from? It's really application of the circle criterion to stability. For this scenario, for the Heavy-Ball method, the circle criterion is equivalent to a jury test. All of these things are lost, they are lost through the years. Eli, does anyone remember the root Hurwitz test? It's the sign of the roots of polynomial. There's a corresponding version of it for, that's the test that people use for continuous time transfer functions. Stability of continuous time transfer functions. For the discrete time version, there is a corresponding test called the jury test due to Eli jury. And this is where these results come, this particular result comes from.
But now that we lost the convexity assumption, don't you need a condition on during the vicinity of X star?
No, that's the thing, right? We can have global convergence, even though that we've lost convexity assumption.
And anywhere on your domain or
Anywhere. You initialize it anywhere, you converge if the ratio L over M is less than that number.
Fine.
Second criterion gives you sufficient conditions of stability. That's why it's a one-sided if. Okay. Now, this is another very misunderstood example. In a paper around a decade ago, the argument of the paper was the Polyak method is not globally converging, and if you're not careful, you end up with weird behavior. Well, that's fine. I agree with the message, but I think the delivery is a bit problematic. Now, let me tell you why it is problematic. So this is the function, looks fairly benign. It is just constructed by stitching a bunch of different quadratics. Yeah. One thing is, I think it is. Yeah. You know, there is this weird thing about the curvature. And if I go and draw the grad of this function, it ends up being this weird gradient, right? Okay. Now, can someone quickly tell me what is the band on its Hessian? It's 25 and 1, right? If I take derivative twice of all of these things, the lower bound of the Hessian is 1, the upper bound is 25. So this is corresponding to m equal to 1. This is the lower bound. But if I look at the gradient and look at how restricted in what is the sector that this gradient is restricted to, I end up with getting m equal to 13. That's the lower bound, and that's this corresponds to the this slope 13. Okay, this is a bit important. So if I go and directly just look at the Hessian, I end up with the biggest sector. If I look at the gradient, I end up with a smaller sector. Now, if I want to think about these things as a robust control problem, if my uncertainties live in a set, which class of uncertainties are easier to handle? The smaller ones, right? Again, but intuitively, it's easier to handle things that live in a smaller set rather than a bigger set. Okay, now let's continue with what I was saying. So the functions satisfy the sector conditions with M13 and 25. Now we have a choice. Okay, let's choose that. Use the sector condition. Pick the Polyak parameters. According to those numbers, we get alpha and beta given there. And we know it satisfies this condition of the theorem and is global asymptotic convergence to the solution. Now, however, if we choose the parameters to be in line with the Hessian of the function, and then we use the biggest sector, we end up with Polyak parameters that doesn't satisfy, these parameters don't satisfy the sufficient condition, and in fact, it leads to a limit cycle behavior. Okay. So this is the dashed lines of the limit cycle behavior. So it's really, I think it's a better example of if you're not careful about embedding your problem class in the right function class, you get the wrong result. I think that's a more important takeaway message than just saying, well, sometimes choosing things in a particular way lead to behaviors that are, they don't line up with stability, and even though this looks very benign. The reason for it that it's a much broader we are asking too much of the method. Yeah.
Would it be easier to break down the function to three and then do like the union of the in your original function, you have three functions that basically that have right?
Yeah, that's exactly what I did in my head, right? I took the derivatives of each of them. I took the largest and the smallest.
So yeah, so like you could systematically always do that if you have a range, like a lower range and upper, and then if you put the union of these ranges, you always get the 13 and 25.
Yes, but the key is, I'm not disagreeing with you, you're absolutely right. The key is that you have to think about the sector conditions to put it together. If you forget that the uncertainty is really a sector-bounded uncertainty, and you try to write everything in terms of the Hessian curve, the curvature band, you end up with a more conservative construct, conservative family of functions. Okay. Now this example motivates us to see whether the heavy ball method converges globally over the class of these functions with the sector conditions. And for some choice of alpha and beta that might not coincide with the Polyak's parameter. Again, we crank the handle of the circle criterion, and we can state the particular result. So for any LMM, if I pick my alpha and beta satisfying these inequalities, then we have a global, uniformly global asymptotically converging system. Okay, so that's that. And then we can push it a bit further. Now we can talk about convergence factors. Again, all of this business is the calculating spectral radius of this matrix for uncertainty parameter delta. We introduced a bunch of algebra. The next slide is entertaining to get things like that. The key is we identify certain regions that, depending on the ratio of LMM, we can find the best and minimize the spectral, that particular spectral radius. If the ratio LMM is less than that kappa naught, which was 3 plus 2 times the square root of 2, the convergence rate is the Polyak convergence rate. For some region between that 3 plus 2 times the square root of 2 and kappa bar, which is 8.29, etc., we have another rule, which is this new function of LMM, which is this other ugly thing. This thing. And then if LMM is larger than 8.29, etc., we get this other formula. The formulas, the exact formulas they did obviously don't matter. The fact that we can have an analytical expression of all these ranges, I think that's interesting. And correspondingly, we have these best choices of step sizes that correspond to those best convergence rates for each of these regions. Now let's look at the picture. The x-axis is the ratio L to M, kappa, for different functions. This is the convergence rate that we get. This line is this theoretical lower band coming out of the heavy ball method. This dotted line is the rate that we get out of the triple momentum method. The gradient algorithm is this upper band. And heavy ball algorithm with these choices of step sizes will lead to this convergence factor that it coincides with the theoretical lower band up until to this point of kappa naught, which was 3 plus 2 times the square root of 2. Then it is start transitioning in this interval between kappa naught and kappa bar. Kappa bar is 8.2. And then it travels around this. So up until this point, in the R convergence sense, it's faster than triple momentum. After this point, it is slower than triple momentum. But there we have to add the caveat. Triple momentum convergence properties in the original paper are proven for convex, strongly convex functions. So if we bring up using circle criterion to prove convergence of triple momentum for this family of sector-bounded functions, we can only prove it for here. We cannot prove, again, it's a sufficient condition. It doesn't mean it's not stable, but we cannot prove its uniform asymptotic stability convergence above this threshold. They don't exactly coincide, but it's very close to the point that these things swap order.
And the theoretical bound is the one that is an extrapolation of the infinite dimension result.
Yes. Yeah. Which we showed that it's the same as the finite dimension one really. Conclusions. So what we did initially, we used the results on the robust gain margin of linear uncertain system to establish this lower bound for finite dimensional quadratic problems. One conclusion that we can follow from this original result is that among all the multi-step methods, Polyak's heavy ball method, in fact, guarantees the best worst case R convergence rate for class of quadratic functions. This happens to be the same band as the infinite dimensional problem. And it follows through that it holds for any class of strongly convex twice differentiable functions as well, because locally they are quadratics. And we're talking about asymptotic rates of convergence, not pointwise in time rates of convergence. And then we introduced this choice of step sizes that make heavy ball method globally convergent depending on what is the ratio L to M for the sector banded non-convex problems. The other thing that we show is that triple momentum is not guaranteed using our results. We don't have the right, we couldn't construct a sufficient condition to be globally converging for the functions in the same sector banded class. And that concludes my talk. Thanks for your time.